Yeah, so let's start now. So let me share my screen and yeah, is my screen visible?
Yes.
Hello, fine. Okay,
Yes, I see
so
your
the
screen.
section that we are about to start now is that yeah, thanks Joseph. Yeah. The section that we are about to start now is learning curves. It is somewhat related with polynomial regression. And so far we have seen till, gradient descent, mostly gradient descent. And in this polynomial regression, what happens? What happens is same linear regression. In linear regression, we will be having the features with the degree 1 degree. We will be fitting the in polynomial regression. We will be adding some synthetic features that will be with some higher orders, degrees of higher orders that will be included, so that it captures some patterns, and then it will reflect in the during training. Accordingly, it will learn, and then it will get it get to know the details. So if you do polynomial regression, if we do that, our training data, how does it impacts the training? So that's what is getting we are getting studying them in the learning course. Here, when our this is the x1 just assume that there is only one feature, and for that one feature, if we make some 1 degree, it's a normal linear regression, then it will be some straight line. But it does not capture the blue color dots are our points, data points. It does not capture all the points, but linearly it try to capture whatever it can. And there will be some it does not there you can we can see we can with visually we can see that the points have very high differences here as well as here. So the distances is very high and it's not better. So then when we try for the second order degrees, that is x1 square and x1, so as some synthetic feature, when we make that, the learning performs somewhat better. The distance is somewhat the last function, the distance is getting somewhat better now. Better in the sense it is getting reduced. The difference between the predicted versus the ground truth, it got reduced. So some learning is better here. Similarly, when we made 300, what happens with 300 dimensions? We can say as some synthetic features, we are adding some extra dimension to the problem in here. So it is trying to capture each and everything in the data. It follows the data point exactly as is. Though some things are getting missed, but the way it patterns is some curves are there, some hinges. It is trying to capture as much detail as possible. It is capturing like that. So here, so what happens if we while making some inference, because these things happens during training. So what happens when we make some inference? If when we make some inference around this point, so for example, some point here, as per the 300
Hello?
We're still here.
Yeah, I think we lost Rajesh Kumar.
Yeah, he's back, I guess.
yeah, is my screen is visible now?
It's still coming up.
Hello?
Not yet, not yet.
Perhaps someone else can share screen and Rajesh Kumar can just walk us through by audio.
That's a good idea. So Rajesh, I can share my screen and is the video back?
Yep.
Or?
Yep.
Okay, good. That's fine.
Can I ask a question while we are waiting? So anyone knows why we give the argument include bias is false for polynomial features? So we would want the constant term as well, right? Why do we give that as false?
It's possible that the polynomial model already includes a zero order term. I haven't looked at it carefully.
So I checked that I checked the sklearn docs. It says if you give it as true, it would add the bias term.
Oh, yeah. Oh, so, but the polynomial model itself, does that include a zero order term?
I'm not sure. I doubt that.
So by putting bias equals to true, you'd be doubling up the zero
Yeah.
order term.
Yeah, that's what I was thinking.
Okay. So where does the bias come from if it's false here?
It comes from the zero order term in the polynomial, because when you define a polynomial, when you define like a second order polynomial, the general version has a constant already in it. So it would be like a0 plus a1x plus a2x squared.
So what does this argument? What's the use of this argument include bias?
Just one question here. Where are you seeing this equation? Like, where are you referring to?
When we
Page
create
133.
Page 133.
The polynomial features function of sklearn.
Okay.
Yeah. So towards to your question, you see how like right now its polynomial features the degree is 2, okay? So if you include bias is false, meaning like you don't have a column for bias. Just be aware. So if you have, let's say if you have that bias that you want to add, which is for example here degree 2. So you're gonna have what? You're gonna have, for example, ax squared plus bx plus c. Okay, so c, for example, here c is the bias. For example, okay, so if it's true, you want to add that column. If you don't have it, maybe then just put it false. So for example, here when they have it false, it's only ax squared plus bx. So there is no c, for example, here.
So you're saying there is no constant term in the equation that we're trying to fit it with?
Yes.
Okay, but that's not good, right? It would not be able. So bias is what actually moves your function up and down. So what if my function is not able to exactly fit the data?
Good. So try to add it and tell us what do you guys actually. I just changed that. Let's change that to true. And but if you change it to true, we want to add like another column though, right?
So I'm just doing it right away because I have the notebook open in front of me. I'm putting the. Can I share the screen for a moment? Okay, he is there.
Yeah. Sorry, team. Sorry for interruptions. So yeah, I'm back. Is my screen visible now or?
Yeah. Yes. But we're just discussing something really quick, Rajesh.
Yeah, fine.
So can I quickly share the screen because probably visually please. I don't find any difference. Just to check.
Yeah. Yes, please.
Okay. Sure. So this I should share the screen.
So if you so I just checked this at the moment. If you run poly features with include bias equals true, at the end what you get after you've done your fit transform, you get like a 3 columns, like I think it was Salim who said it. So before, if you have include bias equals false, you only had two columns, I guess, one for the linear term and one for the quadratic term. But if you do...
what are you saying here? Say for you can see my screen, right?
Yes.
Okay, so here initially this was the thing. Initially it was false. So once I run this thing, this is the output that I'm getting. So here maybe I can take a screenshot, or maybe someone can remember, just visualize this thing. Now I'm changing it to true. I make this change and run this thing. This one thing I can notice visually here, that the hump is somewhere on the left. Now So any visual change anyone can notice?
So hey, okay, okay, sorry, there was a plane just passing on top of me. So what I was saying, don't necessarily focus on the plots. Like try to even and like see what's going on. So as I think Laura or maybe someone was saying, exactly. So like here, what happens? What happens when we add the true? So I mean, I mean, what I'm assuming there, we should have a third column for the bias. So so yeah. So my point, what I'm saying is like the learning curve plots may not necessarily here be the best thing to look at to know the difference. But yeah, maybe somebody else can suggest something else.
So here this documentation says these are the parameters is the including. So this is the include bias is equal to true. So if I scroll through this document, it says include bias is a boolean if true. Then
Yeah, I think I got it. So the way we generated y was just using x squared and x terms. We did not have any other constant term being added, right? It was just the error. So there is no need of a bias term here.
so this
If you,
question is actually of essence here. If true, then includes a bias column. As Salim was saying, it includes a
yeah.
bias column. The feature in which all polynomial pair powers are zero, definitely. And if it's false, it just gets rid of this bias column. It is just as Salim was saying, x to the power n only, where n is not zero.
Yeah. So as I was saying, if it's a general problem, you should always include bias because your data might be above the coordinate axis or below. So your model should be able to move to that region, right? That's how your bias helps. It just moves the curve up and down. But here,
Right.
if you have seen the data that we generated, it was so we randomly generated some x values and we generated y using that. So in that equation, if you see in
So
the
this is
textbook,
the
it's x squared plus, yeah.
this is the data set basically. I think this is the data set, right?
Yeah. So can you go back to the equation where we generated x and y?
Yeah.
That's what I'm looking for.
I think it's above.
It's some random data he will generate. The author will generate some random data at first.
Yeah, that's
Thing
right.
that we are
Just
discussing is,
above. Yeah.
This is
This is
the
the one.
part.
yeah,
This is the
Yeah.
if we
part.
So if
add
you see
bias,
here, y is equal
yeah,
to just using x squared and x. We are not adding any constant terms, right? So that's why include bias is false here. We don't need that bias term. Yeah,
So this
I
is the
got it
bias
now.
term, right? This is the bias term.
That's the error actually.
No, but there is a 2 there,
Yeah.
Gautam. There is a 2. So that's not
Oh,
what you're saying is not quite right. There is
This
a
is the
2.
noise.
So
okay. I did not see
This
the two.
question is the
Yep.
noise.
Yep.
yeah, there is
I
a
did not
This
see
is
2.
the
that.
So
noise.
that's not the explanation.
Yep. Then yeah, it should have been true then. Yep. Yeah, I didn't
Okay,
notice the two. Yeah.
let's check a little bit on this one. Check.
yeah, and the graph that we are trying to visualize is with respect to the training set size and the another parameter.
So I think if we had given bias as true, we should have gotten the answer something close to 2 as the bias value. I think,
Right.
I mean,
Yeah.
we can
Ideally,
check
that
that
should be the
and
case.
yeah.
Yeah. So yeah, let's stop now. Sorry for interruptions. And yeah, so yeah, in polynomial relation we will be adding some synthetic features. Yeah, when we add some extra dimensions, so how our learning it impacts. So it will when the dimensions is 300, when the higher order it is taking up to 300, so it is like adding some extra dimension to our problem. So what happens is, if some validation data comes in, so something, for example, if it comes here something, then there will be much deviation here. It's like it will train very well, it capture, it has memorized everything in the training data, while during the inference part it won't perform very well. So this kind of error is said to be overfitting. It performs very well in the training, and it performs very poor in the inference. And in case of 2, we will have somewhat better. Of course, how it performs in the training, and it's somewhat we can say that it will be better than the 300. It will do better than this 300-degree in inference. But whether it is underfitting or overfitting, that it's trial and error that we have to visually explore. Yeah. In case of this part, the red color line, it does not learn anything very well. Even if we add some other features, some other data points, what will happen is it will extend this line. So the slope of the line will get somewhat tilted. So it may fit like something like this. So the same line will be there, but how much points it will capture, accordingly it will the slope will vary. But it does not the same way. It may or may not. It may underfit. That's the point. And then the author says about that learning curves. The plots of the model's performance on the training set and the validation set as the function of training set size. When we increase the training set size, when we have 0 examples, when you have 10 examples, similarly, what is the validation? So like that, he made some study, and here, when there are no examples, we don't have any error. So when we do some validation, similarly, it will be high at first. When we have some 1 or 2 examples, then the model will learn that very pretty well, but it does not do inference. It'll do the inference very poor. So like that, the model will once it's like when we don't have enough information, we will be like 0. When we have some information, we assume that yeah, this is the only information available. No other information exists. Like that, we will behave. It's not always. It's some moment. Then with that we will continue. Then at some period of time, when we get some other information, then we will update our informations, update our previous informations. Then we will, oh, these are the things that we have to explore, like that. So the model is also like that. Model is like we are training some new brain, so it will learn something, then it will reach some saturation state. After that, even if we add some data, it does not learn. It will just pass through. That's it. Yeah. From this, the author said that this here the difference between the training and the validation curve is very less, and the author specifies that this is underfitting. But I'm unsure about why he is telling that this is underfitting, because in perfect case also we can find somewhat similar, but here why he specifically said this is underfitting, that one I'm unsure. But what we can say is, in the similar case, if we compare this diagram, the diagram here, it will be 0 here. In this case, it is some in this curve, the error on the training, this is a training set size. When we increase the training set size, and the validation error is also getting down, so model is learning something gradually it is decreasing. That also we can find. But
So
in this
Rajesh,
case, the error we can see.
Regarding the underfitting part, I can explain why it is saying that it is underfitting. Because if you
Yes,
can just go to the graph there.
Yes, please. Yeah. Please use annotations.
Okay, just verbally I can explain you. So the thing is that the way underfit works is that whenever you are fitting the data to your training set, so in the training set, what is underfitting is that it is not being able to find the pattern. So basically, the error that is there on the once you come up with the model, then on the training data itself, if you predict and get the output, then compare with the actual training data, actual output. If that error is high, then it's called the underfitting. So here, if you see the RMSE value is quite high. The average RMSE value, once it reaches the plateau, after that, the whole of the horizontal line is quite high. So basically on the training data itself, and you can see the red line is for the training data. So what it means is that for the training data itself, the RMS is quite high. That means the error on the training data, the model itself is making error on the training data itself in first place. That is, it is underfitting. That is why it is underfitting.
Sorry, so are you saying that when the RMSE of the validation set is higher than the RMSE of the
No,
training
no,
set,
no, no,
it's
no.
underfitting?
No, for underfitting, validation does not come into play in first place. Validation comes into play once you go into generalization. So underfitting is something, what does underfitting means is that the model that you have come up with, once you train your model on the training data, then with your training data itself, if you make a prediction, like you are training your model with the training data, then with the trained model, you are once again making prediction on the training data itself. Then the output of this prediction you are comparing with the actual output. That is the RMSE, right? So for that RMSE value, if that RMSE value is high, what does it mean? It means that on the training data, the model that is there, it is not being able to predict well on the training data itself. It is not being able to handle the training data in first place, not to talk about the validation set. So if the model performs poorly on the training data, then we call it is underfitting. So here you can see the RMSE value is quite high. The red curve is for the training data. So for the training data itself, the RMSE value is quite high. That means that this model is not being able to predict well on the training data in first place. This is what we call as underfitting.
Yeah.
Yeah, the
Now I'm able to
question,
relate.
the
Thanks,
question
Srinivas.
becomes, in some sense, the question that people could have is, how do you decide high? Because high could be any arbitrary value. So the answer is
Srinivas,
that.
I will
So
add the point here. Some
eh,
points are here.
just one sec, let me just
Yes,
finish.
please.
I'll yield back. So the point is this, that if you compare two models, one is a more complex model and a simpler model, and the more complex model gives you a lower training RMSE compared to the simpler model, then it means that the more complex model is able to fit the data better, which then tells you that your simpler model compared to the more complex model has a higher RMSE, and therefore the more complex model is able to fit the data better. That's what high versus low means. In that case, you're comparing two different models with two different levels of complexity, which then gives you two training curves. Forget about validation for now, as somebody pointed out. Just two training curves with two models, one more complex than the other, and compare the RMSE of the two. If the one which is more complex gives you a lower RMSE than the one which is less complex, then it means that you have underfitting situation, which means the more complex model better fits the data. So that's how you can tell that by using the simpler model, you're getting underfit compared to a more complex model, which is the example he's illustrating here.
But
When you use this
Srinivas,
ordered,
that will always be true. A more complex model will always get to a smaller RMSE.
right,
so
and that's when
right.
you have to then compare. They also use the validation to say, do you end up with the gap, but at a higher level than without?
Yeah.
But then in this
Adding some
model,
points here.
but there is only one model here. Like there are no two models saying, okay, one is more complex, the other is simpler. Like he used only one model here, and he's saying that the model underfits. Like how did he know it was underfitting?
I think the hallmark of the underfitting is when, when can you say the model is underfitting? It's when the model doesn't, when the model quickly hits a plateau and can't get any better in the training curve.
Yeah.
So you can see that it very quickly, within a few iterations, it reaches pretty much the minimum, which is 2.0, and then it doesn't improve from there. And I think that's the hallmark of underfitting.
But Joseph, that is the case. We will see in the next diagram. That is the case true for the overfitting as well. If you see the learning curve there, the same applies to there as well.
Yeah, but the underfitting situation happens within a few iterations, whereas, in other words, it hits a minimum within a few iterations, whereas the overfitting, it takes about 40 or 50 iterations to hit the minimum.
That's right. That's right for the two diagrams. That's correct.
Yes.
And I can
here.
But then how do we
the
define
validation error at the start? We can see that the validation error at the start is continuing till the end. There is no progress in the validation error. But in this case, if we consider in the below one, the validation area is quite high at the start, and it is getting decreased over the period of time. But in this case, it is almost staying constant. Somewhat the validation, there is no improvement at all in the validation.
So
But
Rajesh,
similarly,
are you saying that for declaring a model as underfitting, we need to study both the validation curve as well as training curve? That's what you're saying.
yes.
So maybe I can add something here. So okay, so I feel this is a very important concept that I feel like everyone want to like have it very clear in their mind. So like maybe a very first simple example. Say you have two data points. Just a line can do fine, can represent those. Now I give you three data points, and I'd be like, okay, just fit the line to the three data points. I mean, you're not going to be able to do that, right? But then if I give you now maybe a quadratic, now you have another degree. Now you'll be able to fit that to those 3 points. Perfect. But now maybe I'll give you a fourth point now. Even the quadratic will not be enough for the fourth point, right? So you can see that like, and that's what we mean by like a simple model, not an enough complex. A model that cannot that cannot fit all the right. But for example, okay, now you only have have 4 points. We'll go back. Now we have 4 points. When I give you a quadratic, you said, okay, no, I'm not gonna fit all of them. But now I don't only give you a quadratic, I give you like a 10th polynomial. So actually it has a lot of degrees of freedom. You'd be able to definitely fit all the 4 points, but it's like you don't need all that, like, but you are definitely fitting them. That's what's like you are even overfitting. So for example, the first plot that he had at the top above this one, I think the first one where he had the 300 and the 10, and that's a very nice plot because for example, you can see how on the 300, yeah, perfect. You can see how on the 300, it was like all over the place. You see like, and that's the thing. And that's the thing. So the 300 will have more power to kind of like fit this for sure. But again, it will not generalize. It will not generalize to the new data points, because what it's trying to do, it went from like finding a function in a way to kind of like just focusing on fitting the data. So this is like a way to kind of just look at this and know when there is underfitting, when the model is simple enough that we can't even, fit all the points, and when it's overfitting, when, So I hope maybe that added a little bit.
Yes, Salim.
So, Salim, isn't that a subjective one? Let's say, going by the example that you gave, let's say there are 4 points. First, you started with a linear curve, which does not fit well. Then, as you increase the polynomial order, it goes on fitting well and well. Now, the point is that at what exact point you declare the model as, let's say, for the third degree polynomial, it is not fitting that well. Now, that, as I mentioned, it is a subjective term, right? So, is there any quantification of this one, that a third degree model, I declare it as an underfitting, and a fourth degree model, I'm happy with it?
Yeah, you see, like one of the other fellows, he mentioned a very good point of comparing the models, and he said, don't worry about validation, just focus on the training. That's a very good way to see like how low can you get. But again, we're only talking about the training to really know again that something generalizes. Then when you also need the validation. So both. That's how you can compare by just looking at the error, and then to know that the model is generalizing, you also need your validation plot. If and anybody please can add to
this. When I see a model that doesn't perform, okay, I'm more concerned about overfitting than I am with underfitting. For me, a model that doesn't perform well is underfitting. Okay, so if you're getting a lousy error number, and you say, well, I would never use this in real life. I mean, my accuracy is 52%. My loss is 12. If you're getting a number like that, yeah, you're underfitting the data. You have to change your model and go to a higher dimensional model for a better fit. And then you go to that high dimensional model, And, you know, going back to the graph that we were all looking at, you know, if you have, you know, random data, you can, you know, take a spline of N300 order and fit it perfectly, you know, but the problem is that the second you go to apply that in real life, it's not going to work unless you have a fixed, you know, data set, because you're interpolating points between what actually exists. And now you've overfit. So, you know, as we talk about today, you know, the different regularization methods, you know, I think it's an important distinction. I don't necessarily think that the curve that we're looking at right there on the screen is the most intuitive one. You know, when you look at the difference between bias and variance, and the difference, you know, and the difference between the validation set and the training set, where it kind of, you know, goes down and then starts going up again, or, you know, the training set goes to 100 while the validation set stays constant at 70. I think that those are much more obvious examples, and I think we're kind of getting hung up on something here.
Okay.
I think that one can actually, from the text right towards the end of this section, you can actually get clearly what the author means by underfit and overfit. And I think the key distinction between the two cases is that there's a very small difference between the training curve and the validation curve for the underfitting case. They both reach a plateau, and the plateaus are very close together, so that the bias is the main driver of the error. In other words, it does just as well in the training set as it does on the validation set, because it's not doing very well at all because of the bias. But then if you look at the overfitting case, now the training error is significantly lower than the validation error. They're both parallel to each other, but there's a significant difference. And I think that's what he says is the hallmark of the overfitting and underfitting, is the relative difference between the training error and the validation error when they reach a plateau.
So basically, as I understand, 2 points here. First thing is that firstly, there is we need to consider both the validation curve as well as training error curve. And second thing is that the difference between the two, if the difference between the two is quite like alike, there is not much difference between them. At the same time, both of the curves are quite high, then we can call it as a underfitting. And in this case, where the difference between them is there is quite a bit difference between the red and the blue, and at the same time, both of them are quite low in their magnitude. That's when we can call it as overfitting. Is that correct?
Yeah, that's what I'm saying. And the reference for that is the two figures, figure 415 compared, that's the underfitting case, compared against figure 416, which is the overfitting case. So here in figure 415, there's a very high error, and it's pretty much the same for both the training set and the validation set. And that's because there's a huge bias that you can't overcome because your model is wrong. So it doesn't really matter, it doesn't do any better, it does equally poorly, I should say, on both the training set and the validation set.
I think, again, I still don't understand the high and the low part. It's kind of hard. I think it's very subjective. But the thing that I remember was that you're plotting this against training set size, right? So it's something like in DL, when you plot against a lot of iteration, you see that the training error would drop and then start picking up. I mean, the validation would drop and then start picking up. So that there is a clear indication of overfitting. Does anyone know or think that it should be similar to this if you were to do SGD, not the closed form solution, because that you can't iterate over multiple times? Does anyone have any experience on that side?
Could you repeat the question, Raquel?
So in DL, once you do, so in this, the difference is the learning curve is plotted, the x-axis is amount of data increasing, right?
Correct.
Whereas in deep learning, when you do it, you plot against multiple iterations or multiple epochs.
Yes.
So there, when you look at validation, it would dip and then start picking up. And there you can clearly say that it's overfitting.
Yeah.
Yeah, can I jump in here? So Raquel, I mean, you have a good point, but I feel now and how we're studying the book, we're more, yes, I mean, because now you're talking about deep learning, but right now let's just try to think even, I mean, I'm not saying that we can't think like that, but because for example, what I mean, okay, to answer your question, for example, in deep learning and you work in computer vision, how are you going to say, for example, that really the model generalizes? You will be eventually to be given it and seen pictures, and it will still perform in them. This is after the validation. But for example, like now here, just like machine learning applications, which can be just like data points, for example, here, just simple data points that we're trying to fit. So what's the new data, for example? A very good way to intuitive way to think of what's the new data. Let's go, if we go back to the plot that we were looking at, the 300 and the 10 polynomial, we can, if you can scroll there. So
right, if you plot that, I totally agree. The diagram on the right hand side with the green line squiggling all about,
yeah,
right?
So with that, what I was gonna say. So let's perfect. So now let's say we're gonna give you okay, the x-axis is from -3 to 3. What if now I'm gonna give you data points after 3, like at 4 and 5? I mean, we're expecting that they're gonna follow the quadratic. That's kind of the right. We're expecting that they're gonna within that. But
right.
but again,
one second. So going back to that, looking at this figure, I think most of us can figure out what is overfitting, what is underfitting, and what is like highly biased and high variance. I think my question is, like, if you look at a validation curve versus a train curve, like, is there some easy distinction to point out whether you're underfitting or overfitting? Yeah, if you look at this curve versus the overfitting curve, like, they look very identical. They plateau out at the same thing.
Yeah.
Joseph made a point about training set size, but again, that is a very subjective matter, right?
Yeah.
Yes,
So
so that's
we can
why
see, right, from the start, we can find that the validation error is almost same from the start. If the validation error is same from the start, what we can think that the model does not learn anything at all. Here we can find that whatever the input I gave, this is what the result, whatever the trained model I'm evaluating. So the validation seems to be constant, somewhat constant. It's like it is same from the start. So the model is not at all learning anything. So if it is not at all learning anything, what we can say that it is called underfitting.
Yeah.
So when does the model stops learning? If it reaches some minimum point, so that's fine. But here what we are seeing is, we are seeing with respect to training set size. When the just assume from here, see from here, when the training samples are 10, the model does not learn anything. Learn anything means, so it is almost same. Even when the training samples are size is 60, some models validation error is same. So this is since if we see the same with here, if in our if it is some different things, for example, if iterations with respect to number of epochs, if we see like that, then we can it will be something different. It may reach global optimum and it is trying to it is not learning at all. That's a different story. But in this case, we are seeing with respect to training set size. So when the training set size is 10, the validation error at training size 10 is same as training set size is 80. So this gives us underfitting in this case. Similarly, if we look at here, the validation error at size 10, it is somewhat high. Okay. So, but it does not remain same still till the end. So it is getting decreased. So this indicates that model has learned something. So it is not underfitting. So we are clear with that. Then how can we say that it is...
I would actually argue that this model is also underfitting, and the reason is obvious. If you look above that graph where he's calling the polynomial regression, he doesn't include the bias term. And I think what we saw before, and people have pointed out, is that when you don't, no, it's just slightly above the graph of 4.16, right. Yeah, just above that, at least in my textbook, it looks like. Right, yeah, it calls it the polynomial regression right there. Go up a little bit, please. A little bit more. Right there. Calling, oops, we just missed it. Go up a little more, please. Right there. Sorry.
It's the code. It's the code part.
It's the curve. It's the code block right above the plot. You need to go up a little more.
Right side
there.
of the screen?
There. Yes, now it's on. So you can see he's calling the, sorry. It's
So
above the next plot. It's the code block above 416.
Yeah, if you go to figure 4.16 and then go to the code block above.
The code block, yes.
Okay.
Yes, right there. So he has include bias equals false, which means that he's fitting it with a 10th order polynomial, but he's not allowing a constant term. And
Joseph,
that's why.
Yeah, actually, when you do linear regression on the features, it adds an intercept term by itself.
Is that true?
Yep.
Is that true? Have we figured that out? Okay.
Yep.
Okay.
Yes, Gautam has, and I agree. I checked it too.
Okay. Okay. Sorry then. Yeah.
Yeah.
But I think that what we're used to seeing is that when we look at when we increase the complexity of a model, we eventually get a model that can actually that the training error can continue to decrease forever, and that's overfitting really. When the more examples you add, the better the training data fits, and we see that in deep learning models a lot. That's overfitting, and so I'm not even sure that. Yeah.
Joseph, I think the important thing.
If I can interject just a minute, the point. So right now, as Salim was pointing out earlier or something, we are still stepping slowly into the more complex domain space. We're just in the linear regression, SDD and stuff. So under these circumstances, it is very likely that we could potentially have high bias, meaning our model, if it is just a linear model, as he's using an example here, may not be able to capture even a quadratic function. Now, to Joseph's point, the thing to understand as we go through multiple lectures in the future is, in deep learning, in neural networks in general, we have a ton of parameters. We are flooded with parameters. So we have even in the most simple case, generally, we have incredible number of parameters. So our problem in general with deep learning is one where it will tend to memorize the data. It will tend often in deep learning, the problem or the challenge is overfitting. That is, because of the amount of parameters, and you have heard that with all this GPT-3, blah, 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 we have millions of parameters. So it's able to capture any function. Therefore, our problem as we go into the domain of deep learning will always, more often than not, be what the doctor talked about as well, which is overfitting. However, because we are still in the realm of traditional machine learning, which we start with linear, go into SVM, even inch our way into quadratic models, we do encounter the problem that it is possible for our model to not be complex enough to model the underlying data. And when that happens, that's when there is high bias.
That's underfitting. Yeah.
And that's underfitting. And when that happens, two things happen.
But here, okay, so here, I still claim, I'm looking at the scikit-learn parameters, polynomial fitting, and from my reading, when you say include bias equals false, you don't get the constant term, and I think that's why 4.16 is showing such a high error. The 10th order model should be able to fit a quadratic function really, really well, and even fit, and it should be overfitting a lot. So I don't.
Joseph, I think you look at polynomial regression, but here if you look at the code, it says you're using polynomial features and then piping that through a linear regression, and the linear regression has the include bias true, which is the fit intercept. So that's what
polynomial features. Now, polynomial features says clearly that if you have include bias
Joseph,
equals
if
false,
you
you don't get the constant term.
If you go to page 129 of the physical book, you can see he has done linear regression on polynomial features, and then he prints out the intercept term.
So polynomial features and polynomial regression, they're two different things, right?
Yeah.
Okay, but are we using polynomial features or are we using polynomial regression?
You're using polynomial features, and we are using linear regression to do the regression.
On that, yeah.
So it has the intercept term.
Created the pipeline like that. But otherwise, what you're saying is right. If we were to use polynomial regression, then there is no include bias, right?
No, I'm looking at polynomial features and in the sklearn, and in the documentation of polynomial features, it says that if you have include bias equals true, you get the constant term, the intercept. Right. But if include bias equals false, you don't get it.
Right, and then when you pass those features to a linear regression function, it adds the intercept on its own. So
yes,
you don't have to,
that's right. That's right.
Yeah. And then I think the major source of confusion here is the graph. The graph here is training set size. So he's gradually increasing the number of examples he's using. And the graphs that we are used to seeing is number of epochs. So if you were to plot number of epochs, and then you could see the telltale sign that is training error is always dropping. That's when you know it's kind of overfitting, and the validation will start increasing. So that kind of signs, those signs you won't be able to see here. So yeah, I think that's why we are a bit confused here. So here the RMSE is not dropping because we are gradually increasing the training set size. It's not epochs that we are looking at, it's training set size. I hope that helps a bit.
Yeah, and I think that what Srinivas was saying is really the key point is that underfitting is when your model model just is not complex enough to actually fit the data.
Yeah, with respect to complexity, we can say, from training sets, from validation set and training set, based on the set size, how it is. So that's what we have in that perspective, from the size of the training set and size of the, as we increase the size, what is the impact of training and the validation. So in that perspective, the author has projected here. Yeah, so looks we are taking, so that's fine, and we will take the discussions further in Slack. So we will just move on for the next one, please. Yeah. So meanwhile, we will be looking at this definitely. So just for time being, due to the time shortage, so let me move to the next one. Yeah, the next one is the bias variance trade-off. The bias is, as we so far we have discussed, that bias means we are favoring something with some wrong assumptions. Our generalization is getting affected. We assume that our data is linear, but the data might be quadratic, so it does not perform well on the data. So this is one such bias. And the variance is, for example, the variance of some numbers. Let's say some 1 2 3. If we take the take its mean, then it will be 1 plus 2 plus 3 equal to 6 by 3 totally, it's equal to 2. And then like this we can calculate the variance. So if some new number is getting added, then what will be the impact? So if the new number is getting added, if it is its mean, then it will be, there is no much variance. If some but higher number is getting added, then it will affect the entire distribution. It's like we are seeing it in one dimension. Similarly, in our training sets, if some other new example if we add, then the model is the model's learning is getting changed entirely. Then we can say that it is very sensitive to the small variations in the training data. So then we can, then that's one sign for overfitting. So we have to whenever we are changing training data set size, we have to check its distribution. Always we have to monitor its distribution. Yeah. Then the next one is irreducible. These are all some noises present in the data sets. The manual way of curating the data, that's the solution for it. So yeah. The next one is we are going to see about the regularized linear models. So for this, what let's see this plot. Here we are seeing that this is some plot for x cube plus the 6x square plus 4x plus 12. So the same graph Yeah, this is x cube plus 6x squared plus 4x plus 12. We can see the same here. If we reduce everything by half, is the graph same or different? So it will be same, right? So this is what when we do the minimization, when we do the optimization, we will try to represent the coefficients using some smaller numbers. So here we can find the same graph. So this is also the same graph. It varies from -2 to 6.1. This varies from -20 to but the coefficients here we can see that this is the lesser. The number is very less. So, it's 0.5, -3, 2, and 6. But if you see here, it's also the same graph, but the value of the coefficients is differing. So it's like same graphs, but different coefficients, some proportional coefficients. In this case, it is proportional because we are considering only one dimension. All our inputs are in just in x. So what if they are something different? For example, here x1 and x squared both are being considered. If we just change them something differently, then so something like that, it will be like somewhat multi-dimensional. It will be changing somewhat bit high level. Close this. Yeah, 3x squared plus 3x1 square plus 4x2 square we are getting. If we plot the just half of them, we won't get similar hyperplane here. We will get similar, but it does not look exactly as is in the one-dimensional case. So that's the point here. But both are doing same some kind of. Once we optimize, we will get somewhat better. So that's the point we are doing in the regularized linear models. Instead of just assume that this is some function that our model is going to getting to learn. Actually, the coefficient it will learn. The x1 is our data, and the 1.5 is some our learned parameters, so, like that. Instead of while doing that, while learning them, also learning the coefficients such that they are minimal, that represents this. So that's what the regularization term comes into the picture. So with this regularization, what we are doing is we are trying to represent the weights of the model as minimum as possible. And for that minimization, what is a function that we are using, what kind of stuff we are using, accordingly the regularization is classified as ridge regression, lasso regression, and elastic net. Okay, in ridge regression we will be doing with the second dimension of the theta square, alpha is some regularization term. So we will try to in addition to our cost function, we will be adding the square of the theta as some additional term here.
Rajesh, one question here.
Yes, so much.
Yes. So in the polynomial regression, the comment that the writer has made, that is quite understandable, that in the polynomial regression, if you go on making higher order terms, then actually you are making a model or making an equation that is more complex. That is understandable. But in the case of linear regression, he is saying that, as you have also said, that to play around with the value of the coefficient. So I don't really understand for linear regression, how come reducing the value, let's say for one coefficient value is 10, for regularization you are reducing it to 5. How does that help to stop overfitting the model?
Yes, yeah. In this case, we have what we have seen is, since it is one dimension, and we are just for understanding, I informed that we are just offing. I'm just making what the point is. The equation that we have seen here, 3x1 square plus 4x2 square is same as 1.5x1 square plus 2x2 square. So both are same.
Right.
Yeah. But how does it impact overfitting? So that's the question.
Yes.
Yeah.
Yes.
So for that, give me some time. We will get the answer shortly.
Okay.
Yeah. It's like we are in this case we are trying to minimize it with some small number. But in the real scenario, since here we are playing one, here in this case, in this equation, we are seeing with, so this 3 and 4, these are some constants. But in our case, it will be some, for each feature, we will be seeing with some different dimensions. And with the dimensions, we will get, the way it is getting projected, it will be different. So somewhat slightly it will be different. It's like what it does is in mean square error, our point is we have to reach the global minimum, and yeah, I'm sorry, yeah, in ridge regression we will be adding this extra feature, so it is like minimizing the square of the theta, and in the lasso regression, it is some absolute value of the theta will be added, and then we will say them as lasso regression. In the next one, that is elastic net. So here we will be adding the combination of both lasso and another one.
One clarification question. Is
Yes,
that
please.
the absolute value or is that the L1 norm?
It's the L1 norm. L1 norm, absolute value means absolute value of -5 is same as both are. Since we are dealing with some vector, we have to say it as norms. Absolute value of -5 is same as absolute value of +5. It's like making everything as positive values. So since it is a vector, they are telling that as L1 norm. For each individual variable, we can say that absolute value. It's like that.
So the term, is it like that the term norm is the equivalent of the term absolute just applied in the case of a vector?
Correct.
Okay.
Correct. Yeah. Yeah. In this, this is L1 norm. Okay. So what happens here is, yeah, when our cost function, yeah, here the 1/2 is added just for simplifying abstraction. So don't worry about that. Don't worry about the constants. Yeah, minimizing 4x squared is same as minimizing the 2x squared. So just for while computing the gradient, this half will be cancelled. So that's the purpose. That may be the purpose. So please ignore the constants for the time being. Yeah.
So let's go back to that question that someone asked about why does L2 regression help? And we're at the right figure 417, where in both models, the purple curve is the ordinary least squares regression fit. So that the purple curve is the optimum closest curve to all those purple points. And on the left-hand side, both on the left-hand side and on the right-hand side, the purple squiggly curve on the right-hand side is the optimal 10th order model to fit those purple points. But what lasso regression does is it says, wait, don't just find me the optimum, but I'm going to mess up your ability to find the optimum by forcing you to give me small coefficients. That's what the that's what L2 regularization does, and in some sense also L1 regularization. It puts some constraint on how big those parameters can be. So so by forcing those parameters to be small, but forcing the sum of the squares of the lengths of the parameters to be small, you get the green curve, which is not the optimal. It's somewhere between the optimal and no model at all on the left-hand side. And on the right-hand side, it reduces the squiggliness of the fit. And then if you make the parameter even more, then you get the red curve, which takes the squiggliness out. It makes it a simpler model. That's what regularization does for you. And the high-level view, as Rajesh Kumar was saying, is that there's 3 kinds of regularization we're considering. One is the lasso regularization, where we're forcing the magnitudes, the sum of the the L2 norm of the parameters to be small. In addition to finding we're imposing that extra constraint. L1 regularization is forcing the sums of the absolute values of the parameters to be small, and then elastic net is a combination of both of those, which gets you the best of both worlds. So I guess yeah, let's just keep going.
Yeah. As Joseph guided, yeah. Thanks, Joseph. Yeah. In this the figure that we are seeing here, it's a ridge model. So ridge model means we should this theta square will comes. So we will be minimizing this extra term also. So in this model, yeah, in the left side, the plain ridge models are used. That is only the linear that alpha value is experimented with 0 and 10 and the 100. On the right side, the alpha values are 0 and 10 power minus 5 and then 1. So this is the plain linear regression model, and this is linear regression model with polynomial features. Yeah. So we have taken this. When we take the when the alpha is equal to 0, then when the alpha equal to 0, then this term won't be exist. It's like absence of the ridge regression. So in the absence of ridge regression, so we will be getting the blue line. Similarly, in this case, polynomial features also, we will be getting the same blue color line. When we add the regularization term, so in this case it is 10, some positive number. So here, if we get some small number, it will be 10 times magnified. So the gradient will get disturbed accordingly. As a result, we will get somewhat different, slightly bit different. It's like adding in case of when some overfitting occurs, we are adding some noise to the noise. As per the noise, our model gets some disturbances. The noise here I am referring here is, it's not to the data, it's to the cost function. So if we add noise, our model will get disturbed. So with the disturbance, it does not overfit. So we can rate somewhat like that. Yeah. Then so like that it is performing. And in the lasso regression, the same case, but here the equation is it's L1 norm. In the equation, we will be considering the L1 norm. Yeah. Then yeah, in lasso regression, it eliminates the weights of least important features. And this one we can see it here. Yeah. So these are all in the left side. You can see everything is our linear model. On the right side, we are seeing it with a polynomial the regression, that model. Yeah. Here one is the L1 penalty and another one is the L2 penalty. This is lasso regression and this is ridge regression. In the diagram itself, we can see, right, this is theta 1, this is theta 2. If we see any equation of the form x square 3x 2x1 square plus 3 2 square. Yeah, if we see them, so it will be like this, something like that. If we visualize it from the top, then we will get contours like this. So that's the plot that we are seeing here. In the same way, since this is a L1 penalty, if we see the same here, Yeah, this is what we will be getting. So in the top view, in the contour plot, we will be getting like this. So that's what we are seeing it here in the left top. Then adding some extra terms to here, some for so this is a lasso regression, right? So in lasso, what we will add some absolute value. So I'm adding the absolute value of x1 plus absolute value of x2. So what will happen here is the contour gets disturbed somewhat. So in this case, it is somewhat perfect. So that's what is it's getting reflected here. Similarly, if we add in the x1 square, x2 square, okay, if you see them, then it will be some compared to the normal this one normal x1 square, we can say somewhat lesser one. So the circles are getting disturbed somewhat. So that's the point here. Yeah, here this is our global minimum. The yellow color big dot is our global minimum when we use L1 alone. Assume that we are starting at theta 1 as 2.0 and theta 2 as some 0.5. We will be starting, just assume that we will be starting from here. So during L1 penalty, what happens is the model is trying to get during gradient descent, it will be descending. Since this is L1 norm, our modulus function, the equation will the diagram will be, it will be like some letter V shaped, and at the point at the end we don't have the differentiation, so that's a different one. So just ignore, let's ignore about that first for some time. And the steeps that it is taking is, it is exact steep. Because of the slope, it will be taking some, if it is some curved one, the step that it will be taking is some small, from here to here it will take, from here to here, like that it will take. So in this case, since it is not curved, it is taking some bigger steps compared to here in the curve. So that's why it is taking at first in it aligned with one dimension, it reaches 0 in the theta 2, then it is moving toward another dimension in the L1 penalty. Similarly, in the L2 penalty, what happens? L2 penalty is like it's curved one. L1 is like letter V shaped. Yeah, in the curved one, and here it the way that it propagates, it's different. Because of its curvedness, the gradients controlling it to move like that. Okay, in lasso regression, it's like adding some yeah, it's like we are adding the extra theta modulus of the L1 norm here in the lasso part. So while adding that, what happened, the model gets started with initially it started with something like here, then after some gradient it started here, then when it reaches the end, because of the steep nature, it will be oscillating from here to here like that if it is in one dimension. So since it's a two dimension, the way it will be oscillating somewhere, and then at over some point it will be oscillating very near to the global optimum point. In case of ridge regression, and here also we can see that the optimal point is here, because we are adding some, it's like we are why? Because this is L1 penalty, this is L2 penalty, and we are adding some extra stuff. If we add some extra stuff, our origin will get changes. And what are those extra steps in our cases? It is some proportion of weights. So here in this case, some alpha, let's say depends on the alpha, these values will get changed. So in our case, since we are dealing, since we are seeing with X L1 with if we see like this, this X1, then modulus of X2, then we will be adding some, let's assume that 1.5 as our alpha values plus 1.5 of our origin gets some there will be some more bias will be there. Yeah, with that our origin gets somewhat deviated. So that's the reason origin gets deviated here. The dark circles are reaching here. In the same case is applicable for ridge regression also. Yeah.
So Rajesh, a question here.
Yes, sir.
So when we are saying, if you go up a little bit for the top right diagram, yeah, the lasso. So in that note that you have highlighted there, actually, you're saying we were saying that when we increase alpha, the global optimum moves left along the dashed line, and
Yes.
when we
Yes,
decrease
yes.
it, the global optimum moves right. So from my understanding, when we are increasing alpha with lasso, it's essentially eliminating some of these weights, the unimportant weights, right?
Yeah.
And so I was just trying to kind of get an intuition for how those are related. Like what exactly is global optimum?
Thanks, Anand, for moving. I do have the same. I don't understand. Since I'm unsure about that. I added a note here.
Yeah,
but,
yeah.
Yeah. So it's
okay.
Salim, Yusuf, and others. Please, I don't have any answers for this. If we increase the alpha, our global optimum would move left along the yellow dashed line, while if we decrease the alpha, the global optimum would move right. So
that's because that's because in the if you had only the L1 function, that would be the curve, the plot on the left. The upper left. That's if you had all L1 and no other function on top of it, right? So so that would be if your L1 penalty, if the alpha gets very high, then you're moving towards a pure L1 minimum right there. But if you now mix in some of the original data, now the optimum from the data starts to take over, and that moves you towards the right. Does that make any sense?
Yeah, I think I'm getting there. That definitely clarifies a little bit. I just wanted now to clarify between what is global optimum versus the origin.
So yeah, the origin is the optimum for the pure L1 penalty or the pure L2 penalty. It's basically saying for example, for the L2 penalty, it's saying that W1 squared plus W2 squared plus W3 squared blah, blah, blah equals 0. And that, of course, is the equation of in this case, it's two parameters, right? So theta 1 squared plus theta 2 squared equals 0, that equation, right? That equation is the equation of circles, right? And so the global optimum, of course, is the origin, right? Making all the weights 0, that's the optimum. And the same thing for the lasso model, the sum of the absolute value of theta 1 plus the sum of the absolute value of theta 2, that's those contours, those square-looking contours that you see. But where is that function minimized? It's when both theta 1 and theta 2 are 0. So again, that's the origin. So a pure L1 model has an optimum at the origin. A pure L2 model has an optimum at the origin. But now but we don't care about the pure models. We're talking about regularizing a solution from some data, right? So there's already some data that says that the actual optimum is at the red point, I think, right? From the data, okay? And so that's the actual global optimum, the red point.
Okay, so in our case, yeah, so in our case, then our objective should be actually the global optimum denoted by the red point, not the origin.
Yes.
Yeah, that's what we're messing up the model. We're messing up the model by adding this regularization term, and now we are forcing ourselves to look for that global optimum, which is the which is the sum of the least squares of the errors plus the regularization term, the global optimum for that problem. And in the case of lasso, that global optimum is that red point. And in the case of the ridge regression, that global optimum is a little bit above that red point, right? It's the same red point. It's also red, but it's a little bit different than the one for the lasso problem.
The other thing which you realize exactly because of what, if you can stay in the diagram, please, for a minute longer, if you can stay with the diagram. Yes, the other insight based on what Joseph explained is, given the contours, you'll see that the lasso lies on an axis. That's because it zeroes out, in this case, whatever the other penalty, and so it lies along one of the axes. You see that it's along the x-axis, whereas the optimum for the L2 penalty lies along a distance from the origin to wherever the L2 values are of both. So that's why the red dot is along the dotted line, which is a line from the origin to that other endpoint. So it will be along a circle that you can draw from origin, because it will be the sum of the squares of L1 and L2, whatever your values end up being. And the L1 penalty will be along an axis because you're zeroing out L1 or L2, depending on whichever is the value you want to zero out to get the better results. And you will end up, that's why you see the green dot go down to an axis and then move left.
Yeah, and also we should mention that in all of these figures, the thing that you should be guided by is the two green squares, or yellow in I don't know if they're yellow or green, but the two green squares. The one on the left is the minimum for the L2 part of the model only, but the green square on the right is the optimum for the model only, without the regularization term, right? So in all four of these diagrams, those 2 points are the same, right? They especially the thing to notice especially is the one on the upper right. That's the model's global optimum, and it's the same in every one of those, right? And also it just turns out that L1 and L2 both have optimum at points at 0. So that's the left hand and right hand green points. And then the red point is the global optimum for the combined model, where you combine the model plus the regularization term. And so on the upper right, that, as Srinivas said, you pushed towards the x-axis, and the global optimum is actually along the x-axis, which means that you've actually eliminated that as a parameter. You now only have a one-parameter model. That's what lasso does for you. Whereas the ridge, the global optimum is both theta 1 and theta 2 are relatively small, but they're both neither of them are 0. It's just push both of them to be small, if that makes any sense.
Joseph,
In this,
I got a
why
doubt
it
here.
has taken this direction? It can take this way also, right?
Sorry?
Here in this L1 penalty, we can see that it has started from here and it reaches this axis. Why don't it reach this axis and then it can deviate? It's also possible, right?
Yes, no, because those are contours. If you look at those contours, you're trying to the steepest descent forces you to go perpendicular to those contours. That's why you're going diagonally downward, because you're doing gradient descent. You're going along the direction of the steepest part of the curve.
Okay.
The other, and it's just more it's exactly what Joseph said, but the intuitive thing is of the two values, you'll go to the 0 first, whichever value reduces or doesn't interfere with your model and still gives the best result, but gets you to 0 and you still get the best model, which in this case happens to be along the x-axis. So that's the other way to look at it as well. But it's exactly what Joseph said. It's just a different way of looking at it.
Yeah, and if you look at the red, maybe it's clearer to look at the red contour that you create, the red and yellow contour that you've created at the right. Inevitably, if you follow steepest descent, it's driving you towards the origin, and you're going to hit either the x-axis or the y-axis, as Srinivas says. And as soon as you hit one of either the x-axis or the y-axis, you now have a one-parameter model. You've eliminated either the x or the y parameter from your model.
And in this case, the distance to the x is smaller, and you zero that out first, and then you're on the x-axis.
Yeah.
Yeah. Sorry to adding another question, please. Yeah. Yeah. An important characteristic of yellow lasso is that it eliminates the waste of least importance. And yeah, this is the point that we are relooking now, right? Am I right? Just for clarification.
Yes.
Yes. Yes. And they call that, what they say is lasso is essentially a dimensionality, or can be considered in some ways a dimensionality reduction technique as well, because of that fact that it tends to eliminate, it tends to drive some of the parameters to 0.
Okay. Okay. Yeah. While starting this,
just one question. One question regarding the L1, L2 regularized model and the global minima, etc. So one doubt that I have is that the minima, maxima, whatever it is an intrinsic property of the data distribution, right? And the L1, L2 regularization and the base model, this is just about the model. These are some properties and some related associated things of the model. Now, if the data distribution is remaining the same, then how come with the change of a model, the global minima, which is an intrinsic property of the data distribution, that is getting affected?
Because now you're saying my model is now not just the sum of the least squares. That's the model. That's the loss function that you would have without doing any regularization, right? And that always gives you the if you scroll back up to the to those 4 blue curves, that model always gives you this yellow point at the top right. That's the global minimum for the actual data and model, right? But now you're saying, okay, I want the model, but I want to add to the model this extra term, the regularization term, which for ridge regression is the sum of the squares of the components, the sum of the squares of the parameters, that is. That's model independent. I mean, well, because it's just the sum of the squares, right? Whatever coefficients you end up with, add a term that's equal to the sum of the squares of those coefficients times some constant. That's the ridge regression. The lasso says whatever the sum of the squares is, whatever the RMS error is, add to it the sum of the absolute values of the coefficients. Again, it doesn't matter. That prescription is model independent. Whatever model you have, you're going to end up with some coefficients. And the lasso term says, add together the sum of the absolute values of all those coefficients and multiply by some constant alpha. So now you have a new optimization problem, and it has a different global optimum, which is given by the red point.
Yeah. Sometimes before, someone asked this question: how does regularization impacts overfitting or underfitting? So now let me clarify on that. Let me add some value points there. If we find without using this regularization, my model will learn something, and then the coefficients will have some values. So in regularization, I am disturbing the model's weights by disturbing the cost function with some proportional values. So the alpha determines how much I am disturbing. So based on the disturbance, the model's weight gets disturbed. So if the model is getting overfitting, so what does it mean? My theta will learn as is exactly. It will give me during training. It will give me exactly. So instead of assigning the exact value, I am just while finding the direction in the gradient, I am disturbing it with somewhat. I am making it to deviate. So those kind of disturbance I am adding here. So it does not learn perfectly. So that's the reason adding regularization will do some add-on in avoiding overfitting. So is it clear? I'm not sure who asked, but I hope it will be clear. Yeah.
Yes, I asked the question. So can you repeat just once a little bit?
Yeah. In our data, in our perfect case, if it is overfitting, our parameters theta will be optimized to find training x's. It will match perfectly with the training x training terms. So we are making the theta to be imperfect in the sense we are not allowing it to be perfectly finding the terms. By how we are doing that, to do that we need to we are making that that disturbance by adding this extra term, the proportional alpha term, not the, we are not disturbing entirely, some proportional of the weights we are disturbing in the cost function, which will cause while computing the gradients, those the values will get disturbed accordingly, so which will impact our optimized theta. So in this way we are not doing some overfitting.
So when you say about it is going to impact,
let me try it also. So by doing the lasso or the ridge regressions, basically what you're changing or altering is the flexibility of the model that you are using. You're decreasing the degrees of freedom. That is, you're decreasing its ability to fit every point in the model. When you do that, then two things happen. One, because you're decreasing its ability to fit every point, and bias is its ability to fit every point, you're increasing the bias actually by doing lasso or ridge regression. But by the same token, because you're reducing its flexibility to fit every point in this sample of data, you're increasing its ability to correctly predict what it will see in any other sample of data. So you're improving its generalization capability, which means you are reducing variance. When the variance reduction is more than the increase in bias, you get a better model. You get a model with less error. That's why when you apply ridge or lasso regression, by what is actually happening is your variance reduces, your bias increases, but the reduction in variance is more than the increase in bias, you get a better model.
That's great.
Actually,
and
it's really well
if you look at the
Okay, and that's
left
the
and
sum.
right curves.
If you get that, then you've gotten all of what we talked about today. That's the bottom line.
so when you talk about the degree of freedom, then for polynomial regression, I can understand if there is a quadratic term and there is a fourth order term, then the quadratic term has lesser degree of freedom than the quadratic term, fourth order term. That's fine. But how the basic idea of general regularization is to decrease for a linear regression. It is to decrease the value of the coefficient. So
exactly, and
we are
by
not actually
doing
reducing.
yes, you're still ready. So let's stick with the quadratic example itself, or even the linear, by actually applying the lasso or the regression and by reducing the coefficient or even eliminating, as you saw in last. So when you eliminate certain things, you're obviously making it, like, for example, I'm just going to oversimplify, but let's say we have a quadratic and we actually eliminate the second term. That means we now have stuck with a linear one. So you're actually reducing the degrees of freedom, but you don't actually always reduce, you always eliminate. So if you use ridge instead of lasso, and in lasso you saw you can eliminate. In ridge, you don't eliminate, but you reduce the weight. When you reduce the weights, then you reduce its ability. It's the same order, but you still don't give it the flexibility for it to flex. By that I mean change as much as you would like to accommodate all the points. That means it can't quite learn or memorize the points, every single point. And that's why it's then able to, and because of that, you're actually increasing its bias, because given a particular set of data, since you're reducing its flexibility, it can't fit what it wants to fit. So its bias will increase. But when it sees a new set of data, then its variance will decrease, because it's not been able to fit this single set very well, it's able to generalize to the next thing it sees better. So when the variance reduces, it reduces more than the increase in bias. That's why you get an overall better model by regularization.
Okay.
Yeah, and if you look at the figure there, 4.18, it illustrates exactly what Srinivas said. So let's start with the right-hand panel, right? And you look at the purple curve where there's no regularization. What is it doing? It's trying to fit all the points in the data, which, you know, we know that those points are noisy, that in a new data set, there won't be that pattern of noise. And so those squiggles that it came up with, we know that those are artifacts of this particular piece of data, and that if you give it a new piece of data, those squiggles are not going to fit it. Because look what happens at the right-hand side. Look where the purple squiggle goes. It's going way down. That's complete bullshit, right? I mean, that's because it's trying to fit the particular data points that you've given it. And if you give it a new data point that goes to the right, let's say, that goes upward a little bit to the right, it's going to do a terrible job fitting it, right? But now, does everybody see that point, how the right-hand side, the purple curve is really trying to fit it's trying to memorize the data points that you gave it. That's what Srinivas said. But now when you force it to do regularization, it makes the green curve, right? You force it to do a little bit of regularization, and now all of a sudden, instead of having this very squiggly purple curve, you'll have this very smooth-looking green curve, which means, and what has happened there is it's actually thrown away. If we looked at it carefully, we'd find that some of those higher order terms got set equal to 0 by the L1, by the lasso regularization process, which we just talked about, right? It's going to force some of those higher order terms to be 0, so now it won't be able to have as many squiggles. It won't be able to fit the data so precisely, and that's why you have this green curve. And then if you keep going and force even more regularization, then it just gives up and it says, I'm just going to fit this with a constant term, and all the other higher order terms are 0, right?
Yeah, very well. If I can add just a couple points here about this, hopefully things that were not mentioned before, because I think everything was already mentioned. You see here one thing to, I don't know if we mentioned it, but one thing to look at the equations, that we don't consider the bias on the regularization term. And please guys, see that how we start from I is equal to 1. We don't start from I is equal to 0. That means we don't really touch the bias. That means actually what we're changing, what we're reducing the size, we're reducing the size of all those thetas, right? And that's why, and he made actually a very good point when somewhere there, but you know, we don't need to go to it, but when he said that yes, yes, we're trying to minimize this. We're trying to minimize this whole cost function. And sometimes that is our performance measure. Sometimes we can just look at that and be like, you know, this is all that we're, for example, the MSE, maybe that's our performance measure, and we only want that error. But sometimes we may, sometimes that can be just the cost function, and then we may use other performance measures like precision or recall or accuracy. But again, so here the first point that I wanted to make is that it's to note that the bias is not included in the regularization term. And to just follow up on Joseph's point, if that hyperparameter, if that alpha, for example, is 0, if it is 0, there is like no regularization. There is nothing there, right? But so it's just not. But then when we're going to start increasing it, what we're trying to do now, we're increasing the hyperparameter alpha, and to make up for that, because what do we need? We need to minimize the whole thing, right? The whole equation. So to make up of the increase of the alpha parameter, we try to put down the weights more and more and more until they get zero. And now they're zero. So what's left? It's only the bias left. And that's why it's a very straight line at that 1.5. If you see that 1.5, it's a straight line there because that's what's left. Everything else is zero. So that's just the first point. And yeah, I think there were other maybe few points that were mentioned, how regularization is really good for noise, you know. So and that's the thing, and that's why regularization is so important in machine learning. Because let's say, for example, now you have all these data points, they're like all over the place. What the regularization add in it tries to reduce the variance because it gives weight. So so yeah, so just to kind of, and if we think so what we can say in better word, then it's paying less attention to the noise. Okay, and this word attention, what's this attention? The attention is really that alpha parameter. That's our attention, how much attention. And I think I hope there was some addition, but that's all. I think there were great points already.
Yeah. Yes, sir. Thanks, sir. Yeah. Followingly, yeah, this is computation of the gradient. So yeah, seen here. So in this lasso regression, we have seen, right? So once it has reached in one dimension, if it eliminates the weights of least importance, then it reaches somewhat zero. So after that, what to do? So if it reaches zero, so at those things, while taking gradient, so we will be using subgradient vector. So that's what the other, if it is a zero, then leave it. If it is some positive or negative, then change accordingly. So like that point is getting impacted here. Yeah. Then the next one is the elastic net regression. So it is parameterized using the value R. It's combination of lasso and the ridge with some proportionates. Yeah. So it is also just some another trial and error. We are trying to get the positives of lasso as well as rigor. So it's like that. And which is good, which method is good? So it's like ridge is good default, but if we suspect that only a few parameters are useful, we can prefer elastic net or lasso. Only few parameters are useful. If that is the case, what will happen is eliminate the weights of the least important features. So lasso will take care of this point. Lasso regression will eliminate the weights of the least important features. So because of that, when the few features are useful, so lasso is preferred. So that's the reason. Similarly, elastic net also. Yeah. And the next one is early stopping. So it's like the number of iterations that we make. So the red color line that we are seeing here is, during training, and this is during validation. Since as a part of our number of epochs, what we can find is our trains get saturated, and our validation error, what happens is it is getting decreased. After a certain period of time, it is getting increased. It's like our this is the point, cutoff point. We can say that our model is doing some overfitting. So those that conclusion is like we can infer it. So in validation loss, it's like it has saturated. After saturation, it is start on the error is getting increased. In other way, our model is not performing poorly on the validation set, but in training set we can find it. What we can find is the error is getting decreased. Okay, so after this point, training set error is getting increased, and the validation error it is getting increased in training set it is getting reducing. In validation it is getting increasing. So it has reaches some saturation point. After that it starts mildly increasing. So this indicates that model is overfitting. So the best model at this epoch number, we can make a note of this epoch number and we can say this is the best model. So when our validation loss does not increase for some n number of epochs, then we can say those epochs as the model at those epochs as some best model. So that's what accordingly we can stop training also. So that's what the author says. Yeah.
So a question here, in such a case then, if we now want to further increase our performance of the model, then is it a choice of just using a different model now because we have gotten to the best that this particular model can give us?
Yeah, with the current hyperparameters, this is the best model. It's a point. Yeah. We may have so all these epoch and the RMSE calculation, this has been done with the current hyperparameters of the model. If you want to try something with the different hyperparameters, then we can try and we can compare the RMSE loss functions.
Okay.
Then we can decide. That's also another one.
Okay.
So the way I like to think of regularization is, has anybody ever seen those? I bet everybody's seen them. The Boston Dynamics videos of the robots that they have that do tasks like pick up a box and move it from one point to another and all kinds of things like that. Remember those videos that came out in the last year or so? And then you see in one video where a worker is beating this robot over the head with a board, right, and keeps knocking him out of the way, and it keeps pushing him and interfering with his performing the task. And the idea of regularization is that, and you can see that if he pushes him too much, if he pushes the robot too much, the robot will fall over. So that's too much regularization. But in between, if you train the robot where he's being battered all the time, but he still can accomplish his task, then that robot is going to be able to be more general purpose. He'll be able to accomplish a task like, you know, in an earthquake, he'll still be able to put the box on the shelf, right? So that's what regularization does. It makes your model stronger and able to generalize better to new data, as Srinivas was saying.
And yeah, so if I can also add to that, so you know how like there is that term that we discussed earlier, the bias and variance trade-off. That's also actually very important to know what's the bias and variance trade-off of our model. And so because, well, what are we trying to always get to? We're trying to get to a low variance and a low bias. And actually, so what now here we're talking about regularization. Regularization helps reduce our variance. So, so yeah, so achieving our desired goal of low bias, low variance. We just want to add that.
So regarding this model training, I've got another question. So how does regularization actually work in real life scenario? Does we always start with a bit of regularized model, or I should not say regularized model, but with the intention of regularizing the model in mind, taking such a model and then start training it? Or we first train an unregularized model. Once we reach the optimum performance of that model, then we implement regularization on it.
Yeah, I mean, I can maybe just say something, and maybe somebody else can suggest this. So you know, like you can have in a way that if you have that term in your equation, okay, and if you have that lambda, for example, is 0, then it's just acting as you don't have any regularization there. So you can just have that as in your equation, and you can now think what's really the right, and I think that was one of the questions here on the chat, what's really the right lambda or the hyperparameter that I want to use. So if it's 0, then pretty much you don't have regularization in your model. But then if once it's not 0, then you are adding a regularization to your model, and then how much regularization you want to add, that's the question, right?
So basically we decide on tune this hyperparameter, the alpha or lambda, whatever it is, we tune that hyperparameter along with other hyperparameters of the model in the same stride, right?
So that's where the question comes. That's what's the right lambda. So again, let's now remember the difference between parameters and hyperparameters. The hyperparameters are what are under control. So yes, actually, we are the ones that we need to find the best lambda, right? Because the coefficients are all parameters. So how to find the right lambda? So for example, here somebody said use grid search. So you want to use a hyperparameter search on that parameter to find the best one.
Okay, thank you.
If somebody has any additional.
Yeah, and the general question you had was that the person had was, how do you use regularization? Do I just fit the model first and without regularization, and then how do I decide to use regularization? But I think in deep learning, the approach that's been developed by most practitioners is, first thing you do is you fit the model, you fit the most complicated model you can, and you deliberately overfit the data, and then you deliberately introduce regularization so that you control that overfitting. So in deep learning, you always want to have some regularization, because you want to build the most powerful model you can, and then beat the model up a little bit, regularize it so that it can't memorize the data, and that it will generalize well to new data. So yeah, in deep learning, you're always going to want regularization, and it's probably good even in classical machine learning like we're doing now to always have some regularization in the model.
And maybe lastly, but that's the thing. If we're going to talk about deep learning, yes, here this lasso and ridge are the common ones now that we're thinking of equations. But then when we're going to start talking about deep learning, there are actually some fundamental different ones. So for example, we can consider dropout is one form of regularization. We can consider, so there are other techniques there as well. But sticking really to machine learning, it's just a term that we're just trying to add to our cost function that will regularize. They will regularize.
And when do you use regularization? Well, when you can't get your validation error, when your validation error is bad, when you have a model that fits the data training-wise, the training data very well, but then doesn't do well when you hit the validation, when you look at the validation set. That means that your model is really memorizing the data in the training set. That's why it can't generalize to the validation set. So that's when you want to use regularization.
Basically, when the model is starting to overfit, that's when the regularization comes in.
Yeah, just to add to Salim's point, even with dropout, essentially what you're doing there again is forgetting. Basically, you're eliminating some of the weights, like making some of the activations 0. So the same concept is basically that you're trying to first let the model memorize and come up with certain weights, and then slowly start taking away some of those pieces so that it's able to generalize better than just memorizing to a specific training set.
Yeah, definitely. Yeah, you can look. Yeah, I agree.
Yeah, I have a question. Does adding regularization impacts underfitting? So, is these regularizations is only for overfitting, right? Is my understanding is correct? These regularizations are only for overfitting. Is there any way to?
That is not going to. It's not going to correct an underfitting problem. If you have an underfitting problem, your model needs to be more complex. So regularization isn't going to help you there.
Okay.
One thing that's really going to blow you guys' mind is that when we actually get to data augmentation, it turns out that a lot of what data augmentation actually does is regularization. I'll leave that for another time.
Yeah, I mean, the same thing. I mean, in general, adding more data to your data set is regularization, has a regularizing effect, because it destroys the ability to memorize patterns in the noise. And that's what augmentation is doing, is it's basically giving you more data. So the general idea is that adding more data is going to regularize your model. It's going to prevent your model from being able to memorize just specific noise in a small data set.
So yeah, so we are. I think this is the right time to make a checkpoint now. So in the upcoming session, we will see this largest iteration till the end of the chapter. So if you have any questions, please add it in our Slack channel, so that our community members we will get it solved. Yeah. So we can close the meeting, right?
Thanks a lot, Rajesh. This was very helpful.
Yeah,
Thank
thanks,
you.
Anand. Yeah, thanks, Anand. And
Yeah, thanks, Rajesh. You've gotten us to the point where we can see the way to the rest of the chapter on next session. So that we'll certainly be able to make it through logistic regression next time.
Yeah, sure. Yeah, thanks, sir.
Thank you.